Okay, hello everybody. I'm just going to check you can hear me okay. Perfect, thank you. So it's Adrian Jackson back again for this afternoon, and we've got two lectures to go through here. The first one we're going to look at vectorization, and then the second one we're going to look at memory operations. And both of these are sort of areas of hardware where it's useful to tune your software for to get good performance. They're both sort of areas of particular hardware in the processors which are key to getting good performance. So that's what we're interested here. Now, as before, if you want to ask any questions, if something's not clear, or if the connections has problems, just let me know. Just send a message in the chat or shout at me. That's all fine. Otherwise, we will go through this. I should also say that there's these two lectures now, and then there is time for practical session after a break. So we should get these first two lectures done in about an hour, and then there's time to come back and look at the practicals. If you have any questions about the practicals or anything like that, then do let me know as well. Okay, so if we look at vectorization, what are we talking about? Well, vectorization is this idea of single instruction, multiple data. So the idea of being able to run one command, like an add, or a multiply, or a divide, or a subtract, which of course are the operations that are key to most of our programs. So have a command that you can run, but rather than just run it on one piece of data, you run it on multiple pieces of data at once. A vector of data. So vector here just means an array, a single dimension array, something where you've got multiple elements, one after another in some kind of storage. These kind of instructions have names because the instruction set that implement them have those names. So you have things like SSE, AVX, AVX2, AVX512, and these are particular implementations of vectorization for particular pieces of hardware. Now, typically a vector will work on, say, maybe 4 bits of data at once, or 8 bits of data at once, or maybe even 16 bits of data at once. Pieces, I should say, rather than bits, because that's a bit confusing. 16 pieces of data at once. There are a range of different implementations of this and a range of different approaches. But of course, you can only use the one that's implemented in the hardware for the processor you're running. So we'll have a look at what's on ARCHER2 particularly. The nice thing about this is it speeds up how much work you can get through for a given instruction, for a given clock cycle. So when a processor issues an instruction, it can do that every clock cycle, every time there is an update on the processor. And then if each one of those instructions actually lets you work on 8 bits of data at once, then you're sort of getting 8 times as much work done out of a processor than if you weren't vectorizing, than if you were doing a serial program where it wasn't working on more than one bit of data at once. But of course, this is not perfect, it's not magic. So there is restrictions on what you can do. So you've got to do the same piece of work on all the bits of data. And that means you've got to have an application, program, a code, which is amenable to that, where you've got the same operations being applied to different bits of data many times. And we'll see what that means in practice. But that's the core idea behind it. You can do vectorization by writing specific instructions that do vectorization yourself. So actually writing the low-level instructions or assembly code or what we call intrinsics, vector intrinsics, and they will say, here, run this vector instruction, here, run this one. Of course, like what we were talking about yesterday, with high-level programming languages, it's not a very portable way of doing things. So if you write a vector instruction for the AVX instruction set, you would maybe have to change that if you wanted to port to a different processor which had a different vector instruction set. So it's not the ideal way of doing that. So we try and focus on getting the compiler to do the vectorization for us. And when the compiler is doing vectorization, for reasons we'll come to look at, it looks to take loops and turn them into vector instructions. And when it's going to do that, it's going to look mainly at the innermost loop in a loop nest, because that's the way the compiler works. Okay, and that's a simple thing for it to do. Compilers can't do, they're constrained by about how much complexity it can do. So what does this look like in practice? So if we have a look here, these bits of code on this side here, we have a loop in C or a loop in Fortran. That loop goes around a number of times. It's specified by this n here, and say that ends 1,000 times. So in this loop, we're going to go through this loop 1,000 times, and each time we load up a different bit of B and C. We do an add operation on those bits of B and C we've loaded up, and we store them to A. So we've got two loads, an add and a store, and exactly the same instructions, two loads, an add and a store, two loads, an add and a store, will be done every time we go around this loop, starting at 0 and all the way up to n. We'll do exactly the same instructions. So this is the kind of thing where we can easily say, well, actually, instead of doing the operation on B0, C0, and A0, and then B1, C1, A1, you can actually do it on B0, 1, 2, and 3 at the same time. So you load up B1 to 3 and A1 to C1 to 3, and you add them together and you store them into A1 to 1 to 3. And that's what the vectorization is doing. So it's a special bit of hardware, which instead of working on two bits of data like this and producing a single chunk of data here, you can work on 4 chunks of data at a time and produce 4 chunks of data at the end. There are the processors we're using in ARCHER2 have this AVX256 instruction set, which means it can do 4 64-bit numbers at once or 8 32-bit numbers at once. It also, and you may or may not care about this, but it also has a latency of 6 cycles. What does this mean? Well, this means that when you issue a single vector instruction, it takes 6 clock cycles before you get the result of that instruction. So the vector unit is pipelined, it's got multiple stages that have to work in it. So when you start a vector operation, there's then 6 cycles before you get the result of that. And so you could say to yourself, well, what's the point in having vector operation which does 4 things at once if actually it takes 6 times longer to do actually overall? It has a pipeline of this in this vector unit. So if you start one instruction on the first clock cycle, then it moves on to the next stage, and then you can start another instruction, another vector instruction, and you can get to the point where you have 6 instructions all run at the same time. And once you've got that, you would start producing a vector result every clock cycle. And at that point, then you're getting 4 times as much work out of the processor by using vector operations. You know, long and short of it, you don't really care how it's implemented, but this just means that vectorization is only going to give you good performance if you have enough work to keep that 6 depth pipeline full. So really, vectorization will give you good performance. Go back, if n here was 8, so I've got 8 iterations here, that would turn into 2 vector instructions of 4 each. So we've only got 2 vector instructions coming out of that. That's not enough to fill up that pipeline in such a way that I get good performance out of it, because it would take me 7 cycles, 6 for the first one, then 1 more for the second one, because it's gone through the pipeline, to get those 8 instructions. So you're not getting really very much speed there. So if that n is 1,000, then you've got much more scope for speed up, because after the first 6 instructions, you're then getting an iteration, a result every cycle. And so vectorization only gives you good performance for relatively large operations as well. So as I say, what we're interested in is having a compiler do the vectorization for us. That means there are things we can do to help the compiler do that vectorization. General guidelines around what can vectorize easy and will struggle to vectorize. Compiler understands what hardware it's building for. So yesterday we talked a little bit about the compiler you build for architecture, for a particular instruction set architecture. And that's important to make sure that the compiler knows what instructions to build for. Now, today, compiler usually will mainly loops. So the loop, I can see here there's some operation that looks like some loop. So apologies, I think I dropped out there. Apologies, I think I dropped out there for a minute. The connection must not be brilliant. So I'll start again and let me know if I've missed anything out here. But the compiler will generally only vectorize loops, and it will only vectorize the innermost loop in a loop nest. So if you've got a loop inside a loop inside a loop, so you've got a for loop and then inside that another for loop and then another one, which often you will have with multi-dimensional arrays. So if you're, for instance, working on a 3-dimensional array of data, then you might have a loop to go over the different dimensions. Why do we care there? Well, usually because the compiler will only vectorize the innermost loop, you want to make sure that that one has got enough iterations to be worth vectorizing. So you may have to reorganize things to get to that stage. And the compiler will be looking for certain kinds of code, and we'll come on to look at what that means. So the compiler will look at loops, try and work out if the loops are independent and vectorizable. And if they are, then it will do it. And if they're not, then it will not. And sometimes the compiler can be quite conservative in what it considers can be vectorized. So you can do some changes to your code to improve that. How do I know if my code has been vectorized? Well, again, you can have a look at that compiler output we talked about yesterday, where you can get it to produce you a report of what is done, and it will tell you if things have been vectorized or not. You can also have a look in the assembly code it generates, and then see particular instructions, vector instructions, and using particular registers like these vector registers. If the compiler is looking to do the vectorization, it will be looking for loops that have a determinable trip count. That means that n I had on my for loop, it needs to know how big that n is. So it won't, you don't know when the loop's going to end, because it's very hard for it then to do multiple iterations of that loop at once. Vectorization is very much like that loop unrolling we saw yesterday, where instead of doing one iteration of a loop, you're doing 4 iterations of a loop. And you have the same kind of issues that are associated with that. With if a loop count is not divisible by the vector length, you have to do the compiler has to do some work to deal with that. Compiler will also not vectorize well loops that have some functions or subroutine calls in it. So anything that's being called inside a loop will stop the compiler doing that, unless it's one of the basic things like a library function from a maths library. Or if it can inline, if it's a small function, it can inline it, then that can also help the compiler vectorize. And then it doesn't really like branches or jumps, so conditional statements inside the loops as well. And again, that's very much like what we saw yesterday with the optimization. If statements inside loops can make it hard for the compiler to optimize those loops, it can also make it hard for the compiler to vectorize those loops. The other thing that compilers will look for, and this is very similar to shared memory OpenMP style programming, is dependencies between loop iterations. So again, the compiler is effectively doing a parallelization over your loops iterations. So it wants those loop iterations to be independent to do the vectorization. And so dependencies in the loops, like a variable which is summed up across the loops, makes it hard for the compiler to identify that this loop can be vectorized. It also has the same kind of things we saw yesterday around pointer and pointer aliasing. And so if you're doing C and C++ codes, you may want to use this restrict keyword, which can tell the compiler, oh, actually all these arrays are separate. Now you can check with these compiler optimization reports. Then go and help the compiler by adding directives or changing your code. If it's not really talked about yesterday, but is important in this context, is what we call alignment. And so alignment is really how is the data you want to vectorize stored in memory. Contiguous blocks of memory, so chunks of memory, one at a time. And so for the vectorization to work, you want your data to be stored in a contiguous chunk so that the compiler can load it up and easily access it. Processor can load it up and easily access it. And in that context, what we say is we want the data to be aligned. So to lined up with particular boundaries in the memory, which makes it easy and quick to load up. And we'll see how you do that. And then finally, iterating around these things, and we're trying to load up data. We actually want our so if each iteration of the code goes, if we go back to our simple loop over here, if each iteration here is going 0, 1, 2, 3, 4, that's a unit stride. So if I'm iterating from a loop here with a unit stride, I go up by 1 each time. The next bit. Now, from the compiler point of view, what do you need to do to make sure it does vectorization? Well, it depends on which compiler you're using. So for the Cray and the AMD compilers, they will vectorize with the default vectorization. And so march equals zn2. This is a way of telling the compiler this is the way this minus F no vectorize flag. And that's a good way of being able to say, is my code vectorizing well? If I compile it without vectorization and then compile it with and compare the performance, I can see how well that's giving me a performance improvement. And then the Cray compiler will give you things like the performance optimization reports that tell you whether it's done a good thing using these flags down here. And the equivalent flags for Cray Fortran off the GNU compiler right here. So if you want to look at what a compiler's done, you can use these flags to do that. Exactly like this here. There are also other things with the GNU compilers. So there are other flags here that you can use as well. So these optinfo, vectorized mist, all these kind of things. So they all do similar things, but you can get useful information out of them about how well the compiler is vectorizing your code. As I say, when it's looking for vectorization, it'll be looking for things like this. Are there dependencies between iterations? To this looks like a dependency here, so the compiler won't vectorize it. If you look at those optimization reports and it says couldn't vectorize this loop because there's a dependency, and you look at it and you yourself realize there is no dependency, it may look like there is one, but there isn't, you can tell the compiler that it's safe to vectorize that loop with some commands. If there is a dependency like this one here, you could re-engineer code to get out of it. So for instance, you could turn total into an array, and you could create an array of totals, a separate one for each iteration of a loop, and then at the end you could do a sum of them in a loop that's not vectorized, but will let you vectorize the main loop as well. Look for things like, are the individual bits of data independent? And so this is an example of a C code where the compiler would struggle to vectorize it for a number of reasons. But one of them, the data 1, data 2, data 3, which are being used in a repeated loop here, and or data. It doesn't know because these are pointers, and pointers can be set up to all in them. I also won't like this because this loop size thing here is a pointer, and that means it could be changed as you go around the loop. Even if in here we don't have something called loop size in here, J like that may actually, well, not J, but data 1, data 2, data 3 may actually point somewhere. So compiler has to be very careful that it doesn't make wrong assumptions and so vectorize that loop. So there are things you can do here. You can use this restrict keyword in C and C++ to say, well, these are pointers, but I'm telling you as a programmer, they all point to different places. That's what this restrict means. You could also take that loop variable and turn it into a static variable at runtime, and then use that here, and then it'll be much clearer to compiler that this is not going to change as the loop goes round. And then this thing here, this #pragma ivdep, tells, this is for the Intel compiler actually, but this tells the compiler that that loop is independent. So even if it looks like it's not, because there's a J in here and it's coming from an index and we don't know what that means, I can look at it as a program and say, oh, actually, I know that index I is always going to be in a sensible form. So you can use things like or this one up here, #pragma clang loop vectorize enable, which will allow that loop vectorize. So an example here where this loop doesn't do, the compiler won't do a good job of vectorizing this loop because of the structure of it. This is in Fortran, but the reason it necessarily vectorize this loop here is because of this X variable in the middle, where because X at iteration 1. and so there's dependency there. But you can refactor it out and again turn that X into an array of a single variable, create those arrays as we go around, and that will get rid of that because each one of these X's is independent, and then, you know, there isn't the same level of over between the there instead. And looking at some old examples, exactly the same thing, but looking at what the old Cray compiler would have done with this, it would tell you something like, well, okay, here, this loop not vectorized because there was a redundancy found on Y, loop was out and get vectorized. This overlap is used, that's what this recurrence means here. Whereas if you rewrite it and change it to that, then it will tell you, okay, actually, I can vectorize that, I can vectorize that, I can unroll loops. And in this example, it went about 4 faster. There has to be some work done to move that cache data to a register and make sure it ends up with instructions. If you don't have aligned data, it has to generate 3 versions, one called a peel loop, one called a kernel loop, and one called a remainder loop. And the peel loop is the set of iterations. And so it'll do some serial iterations to start with, before it gets to a point it can run your vectors. Then it'll run the main loop where everything's lined up and it's good, and then the remainder is the bit to deal with that overhead of you know, the number of iterations that don't fit into the last vector instruction, so you have to do those in serial. If you can get this data aligned, you only need 2 versions of each loop. You don't need that first peel loop, you just need the kernel and remainder loop, and that gives you better performance. How do we do this? How do we do the alignment? The alignment you need a special way of creating the variables in the first place. So there's this thing called _mm_malloc and _mm_3 for C programs, which will do that alignment. So here it's creating a variable called A, an array called A, and it's 1024 elements, and it's aligned on 64-bit, 64-byte boundaries. That's what it's doing there. You can also, for Fortran, because you don't usually use these malloc and free things for Fortran, you can do these allocatable things where you create the array here, and then afterwards you say align that array, and the compiler will know what to do. It's also possible to do this on static arrays in C, in exactly the same way you do it in Fortran. And then there are other things you can do as well, but often covers it, and more often, you know, it's sensibly. There are other ways of doing this alignment, other functions you can call. So aligned alloc is equivalent to mmmalloc as well, aligned alloc. You also have to be a bit careful about multi-dimensional arrays to make sure they're aligned. So in this case, creating 2-dimensional array, we're actually going to create it as one long array and align that. But that's going to be, you know, that if you did it like this, then you may not actually end up with aligned elements when you go down to this, because the innermost loop would say, you know, that's maybe not lined up properly. So actually you would want to do an mmmalloc of each dimension and do that separately. That's just something to be aware of. Strangely, when you do this on the compiler, you need to make sure you create the variables, the arrays you're using as aligned. And then once you've done that, you also then need to tell the compiler you've done it. Now, this seems a little bit strange. This may seem like a counterintuitive because you've already done it. So why do you need to compile again? If you're using what you did was align the data so it can assume it's aligned. And so you can use these commands in code here, assume aligned or vector aligned, to tell it that this is the way it's done. You can also use some OpenMP commands to do it as well. So this OMP pragma SIMD aligned will do the same kind of thing. There's some more things you can do with Fortran, but we don't need to go into huge amounts of detail there. If you're interested in that, let me know. But there are some things. Yeah. If you need that detail, let me know, and I can go through it, or I can let you know what's the thing to really bear in mind there. As I say, OpenMP also has a way to do this vectorization as well. So rather than using the compiler, you can also manually specify vectorization, but through a portable way, so through OpenMP. This is not doing the threaded parallelism, this is doing the vector parallelism for you. And so you can put this hash pragma OMP SIMD or for C, or bang dollar $OMP SIMD for Fortran, and that will do that kind of thing for you. And there's various different things you can specify when you do that. So if you have some examples where the compiler is struggling to vectorize your loops, but you know they are vectorizable, then one way of doing that is to use these OpenMP variables instead to tell the compiler, okay, vectorize this loop here, and it will go and do that for you. So just a couple of more examples to round this off. As we mentioned before, this is a Fortran loop, but this is we've got an if variable inside this loop here, so it's going to struggle to vectorize this because this if variable disrupts the optimizations it can do. But you can refactor that, get rid of the if variable with extra work, and then this loop is given 0 is for a certain part of a loop, and then at the end of a loop, so effectively what it's doing is going all the way down here and then initializing the first value of the array. And here what we can do is just take that away in a slightly different way, iterate over the loop slightly differently, and then initialize that final value. And this bit in the middle here then should vectorize. Another example here is dependencies in the loop. And so these d alpha and d beta here look like they're dependencies in the loop because they are being reused each time we go around, even though we're not necessarily keeping track of the overall values. And so they can often prevent vectorization. So then again, you can turn them into arrays again. So it's d beta and d alpha arrays. You create those over time, and then at the end, you create the final value you want, and you don't worry about the vectorization of this one. You vectorize this more expensive loop here, and then do a second loop over here. So we've traded off memory here, so we're using a bit more memory to store these temporary values, but we get performance improvements because we're changing, we enable vectorization. So there is a practical on this, which should hopefully make it more clear because you go through some little examples and you can play around with doing this vectorization. But if you have any questions on the vectorization, if not, we'll move on to the memory lecture and we'll talk a little bit about memory layouts and memory structures. And then after that, I can let you get on with some practical. Okay, so the other big topic for optimization, we've had compile, we've had vectorization. The other big is the memory, usage of memory and caches to get good performance for your application. So memory is the area where we have a big impact on performance, because memory, getting data to and from memory is slower than doing processing. So for running the actual instructions themselves. This is why we have caches in processors, to try and bridge that gap. Caches are small but faster local memory on the processor, where you can store temporary data before whilst you use it, and that can reduce the impact of memory being slow, because you have this temporary data stored locally, which is very fast. So making sure that you get your memory structures and your memory usage correct, and set up in such a way that it uses the cache and the memory hierarchy well, can make a big difference to your program's performance. So from your perspective as a programmer, you're specifying to the compiler what your data and memory looks like. So you're specifying what your data is and how it's going to be used. Now the compiler can do some work to change what you've specified, but it is constrained by how you've told it you want the data to be laid out in memory. It can put a bit of padding in to maybe change the size of some arrays or some variables, but beyond that, it is very much constrained by what you've told it to do. And so you changing your program, or making sure your program has efficient memory structures, will help the compiler do the optimization, will help you get good performance. And of course, there are different types of data structure. The ones that we're often most worried, concerned with or focused on for scientific programming are arrays, because that's what we tend to have, these large multi-dimensional arrays where our data is stored. But there are other ones, trees, lists, objects, pointers, those kind of things, which can be used in scientific codes as well. The reason arrays are useful is because they are good at representing discretized versions of continuous data. And they'll look something like this. This is a Fortran array, three-dimensional array, 100 by 100, where we access it with these brackets to get it, the different indexes, the IJK index of this here. So we can get a single, or we can set a single bit of data like this. You could do exactly the same thing by creating a one big single dimensional array and then indexing it across like this. And conceptually, these two representations are the same, but from a programming point of view, the one on the left here is much nicer. And in reality, when you write it in the left, what's done in the left here, the compiler will turn it into something which does what's done on the right here. So this addressing into the different indexes like this. Same on a C program at the bottom, or a C++ program. I've got an array, static array, 100 by 100 by 100, and it's functionally equivalent to this one over here. So as we saw in the vectorization lecture, you often have data access patterns where we loop over array elements, and that means we get, we understand what bits of data we're accessing and what bits of data we're accessing next. And if we can loop over those in the order they're stored in memory, then we get our best performance, because we are going to load up data in contiguous chunks which match our cache lines, and we get a minimum number of cache line loads for every bit of data we need. Again, what does this actually mean in practice? It's all very well and good to say that. This varies across programming languages, but if we took the one at the bottom here, this is C. For C, then going through this rightmost dimension, the J dimension here, in this two-dimensional array, going through this J thing here, will give you, as the innermost loop, will give you the best performance, because all the elements on this J dimension are stored contiguous in memory. And then when you go on to the next I, you go on to another block of J's. You go on to the next I, you go on to another block of J's. So for C, this kind of loop ordering and indexing is going to give you the best performance, because that J is the contiguous dimension. If you can write exactly the same code here on the left, and it will work and it will run, but it will be slower because you're going over this I dimension the quickest. You're doing many more loads of chunks of data to get your individual J elements, and so you get much more memory traffic here. In Fortran, it's exactly the opposite way around. The leftmost dimension is contiguous in memory, so you want your innermost loops to be going over the leftmost dimension, not the rightmost dimension. So this formulation here on the right-hand side is much more efficient than this formulation here on the left-hand side. These were all assuming we have fixed size arrays like these here, so we know at compile time how big the arrays are. You can't always do that, so you often need dynamically allocated arrays where you create them at runtime based on some parameters that you pass in. That's also fine, and the same thing usually happens. You've still got the same contiguous dimension, one which is the fastest to go through as well. And so you can do things like this, where you can do a two-dimensional array which is static and then allocate a bunch of those and then go through it in this kind of order here, and that will still give you good performance there as well. One of the more common ways of doing it dynamically in a programming language by C is to do something like this, where you have multi-dimensional pointers and you create arrays of arrays of arrays, and then you can still access them in this way here. And this will give you the best performance here, because the k-most index is the quickest moving index, and it's the one where you've got the actual data structure contiguous in memory. So this one here is allocating a block of n floating point numbers, and then these ones here are allocating the pointers to keep track of multiple dimensions of those. C, you can do this multi-dimensional indexing like this, this is a very minor point, but this kind of indexing here can take a little bit more take a little bit more instruction to get to the data itself, because you have to look at each one of these pointers basically with a pointer chasing to go through here to get from the first dimension to the second to the third. To get your actual data is equivalent to this set of instructions over here, and that means you're going to do a little bit more memory accesses to get your data out of it, but it's still perfectly possible to optimize and vectorize and get good performance then as well. So that's the most important aspect of scientific programming for memory, is this idea of making sure you're iterating over the data in the order that it's correctly stored in memory. There are, of course, other data types, and so you can have a structure or a user-defined type in C and Fortran, and these can be very useful for programming because they let you collect together, for instance, you've got a particle and you want a particle to have an X and a Y and a Z coordinate. You can create that into a structure so each particle has an X and a Y and a Z. So from a programming point of view, that can be very useful. And yes, it can make it nice. The problem is that can impact some of these performance issues where you want to get the data in the right order to get good performance. And then because the compiler will, so this is an example here. This is a structure here. It's a particle, you've got an X and a Y and a Z, and then you've got an index and a mass. And what the compiler will do is it will create an object like this, and then in memory, X and Y and Z and index and mass will be contiguous in memory. And then you'll move on to an X particle, and then it'll be X, Y, Z index mass, X, Y, Z index mass. Now, from a programming point of view and a software engineering point of view, this is a very nice way of doing things over here. But you could imagine if you're going to do some calculations where you want all the X values and all the Y values, or all the mass values, then this means you've got to load up chunks of data. You've got to load up X, Y, Z index before you get to mass. And so you're loading up 5 things when you only want one of them. So this is an array of structures on the left-hand side. The other way of doing it could be a structure of arrays, where actually you have all the particles is the type, and then inside that you've got an array of X's, an array of Y's, an array of Z's, an array of indexes, an array of masses. And then if you were just going to work on the mass, you could pull out that whole array. It would be contiguous and you would get better performance for that. So you can have some influence over the performance of your program by deciding how you structure your data sets and your data with one eye on the fact that, okay, I know I'm going to spend all my time working on the mass, so maybe I want that contiguous. Or maybe it's when I get a particle, I need X, Y, Z index and mass all at once. So actually this way is the best in doing it. So thinking about how you're going to use your data structures and what impact they may have on memory loading and storing performance, that is a useful thing you can do as a programmer. So, this array of structured posts have a good if there's lots of computation on each element in the structure at the same time. Bad if you don't do that, and don't map very well to vectorization, but are very nice from a software engineering object-oriented design point of view. Whereas the other one we saw, the structure of arrays, has much better spatial locality for all the individual elements of the structure and may vectorize better, but maybe isn't quite as nice as design as before. You can actually also do something called a structure of array of structures of arrays, where you do some mixture of the two, where you have a small set of arrays which will map to a vector as well here, and then you have an array of those. And that, once we're getting down to this level, we're into some quite specific engineering design, performance engineering. So sort of you wouldn't get to this level without having done a lot of work on the code, but you can think of other structures like this which can maybe map better to the hardware you have access to. There are also other things like objects in object-oriented programming, like a C++ program, which can have other data structures which can also impact performance. There often can be overheads for associated with accessing these structures or updating the parts of these elements. Now, again, most of the time you don't have to worry about this. The compiler will get around this. But if you've got lots of small objects with lots of small amounts of data in them, that can impact things like vectorization or data loading and storing costs. And then if we go beyond this, we've got things like trees and lists, which can be very nice ways of storing data because you can grow and shrink these structures. You don't have to create one big array at the beginning of a program. You can create an array of linked lists and add new elements when they come up, and that can be a very nice programming approach. But it's quite hard to then get that contiguous data access and then get that vectorization performance that you would like. There are higher level ones as well. So there are higher level data types you can use: lists, trees, sets, maps, those kind of things. And they can be optimized for reasonable performance on languages like C++ as well. So in terms of memory performance, we've had a look at some of the things that can go wrong. So it's lack of spatial or temporal locality, that is going through memory in the wrong orders, can really impact performance. Unnecessary memory accesses like pointer chasing or having temporary arrays that you don't really need. You could recalculate values, can also impact memory performance. And then some of the things we saw around vectorization and optimization, where the compiler doesn't understand what your data structures are doing, so it can't do good optimization. So a program can also impact performance, and this is sort of overlapping or aliasing of pointers and alignment of data structures as well. There is possible to, because a lot of codes on a system like ARCHER2 are what we call memory bandwidth bound, so they're limited by the amount of data they can store or load to and from memory. You can often optimize codes by going through and getting rid of some features which trigger higher data storage overheads, data load and store overheads. So things like unnecessary pointer arrays, where from old codes you can quite often have linked lists that could be arrays, or pointer arrays, it could be simpler static arrays, or temporary variables where you calculate a value that's quick and easy to calculate and then store it for the lifetime of a program and keep looking it up. Might be better these days going back and replacing that with just recalculating every time, because calculations are cheap and loading and storing memory aren't. Even sort of these lookup values here, lookup tables, if they're cheap to calculate, it might be a good trade-off not to actually store them in a memory structure, but actually just to calculate them each time. Now, of course, there's no perfect answer here, because if something's expensive to calculate, then it's probably worth calculating that once and storing and reusing it. And so there's you've got to understand the nature of your program and how costly things are to calculate, then work out what your strategy would be there. Getting best performance out of a memory system really does mean using this cache approach efficiently, and so the contiguous memory thing that we've talked about is one of those mechanisms to do that. But yes, so there are other things that you can do to improve cache performance as well. So avoiding unnecessary gaps in structures or having variables close together can improve performance reuse of these kind of things. And there's also some extra optimization techniques we can use to reuse data in caches. So there are these ideas of strip mining, loop interchange, or cache blocking, which are all very similar things, which are designed to reuse data that's already been loaded into cache in certain ways. So we can have a look at, you can have a look at how big the cache is on something like ARCHER2, and then have a look here, because we're going through this data structures A and B in different orders, so we can't ever line up them both so that they're both contiguous in memory, because we need to do this ij for A, but the B side is ji. That means that we're always going to get poor locality for one or other of these. We can reorder the loops, but it will impact one or the other. And often, this looks like a stupid thing to do, but often you might need to do that for, say, some matrix operations where you're transposing an array or doing a tridiagonal or something like that. And so the idea here is that you can do some cache blocking or loop tiling, where instead of going all the way through the memory like this, you go through it in little chunks. And then for that little chunk, you're reusing the bit of the other array which you don't have good locality on. So you're not having to trigger as many loads and stores on the non-contiguous one, while still getting good performance on the contiguous one. So that can be quite a nice approach to do these kind of optimizations as well. This is also an example of doing the same kind of thing, but for a vectorization, so you can do a bit of tiling for vectorization here as well. So in this top example, because you depend on the previous iteration of aij, so aij minus 1, it won't vectorize this because the compiler sees these dependencies here, but you can reorder the loops here, which is now the non-nice order for caches. You've got the J here, but you can have a little block inside here where you've actually reordered the accesses around what you're doing, so that you don't have to rely on these dependencies impacting your vectorization. You can also do things like make sure that you fuse loops together so that you can reuse the data across them. So here's an example in Fortran. We've got two loops here doing different things. This first loop here creates A by taking a B array and timesing it by 2. And then this second loop over here takes that A array and then adds 1 on it. And both of these are perfectly fine. There's nothing wrong with these. But what you do in this first loop is you're going all the way through that A array. So by the end of a loop, you've gone all the way through the A array. It's been loaded and stored to memory as many times as it needs to be. And then you get to the second loop here, and then you go all the way through that A array again. So you're going through that memory twice. Whereas if you fuse those loops together and you do both operations in the same loop, this A will still be in the cache when you come to do this operation here. So you only have to go through that A array once, and you halve the amount of memory operations you have to do for the A array. And you can also do a blocking of that, so you don't have to do the whole thing. You can do a subsection of that loop. So you can do a small bit of a loop, and then a small bit of the next loop, and then a small bit of a loop, and a small bit of the next loop as well, depending on what you're trying to do and the complexity of the memory access patterns there as well. There are also, so this is getting into looking at your program, working out where the memory issues are, where the performance issues are, and then saying, look, can I restructure my code a little bit? Maybe restructure the loops, combine the loops, maybe restructure subroutines so that the bits of code working on the same data are in the same place. And those are things like removing, combining bits of code as well, putting the loops, combining loops, combining parts of loops, those kind of things, getting the compiler to inline functionality, just where you get to the point where you are loading and storing large chunks of data, large arrays, the minimal number of times. So there's no perfect way of doing this, but it's a question of finding the part of your program which is expensive through profiling, through performance characterizing, then having a look at it and saying, well, okay, why is this expensive? Oh, we've got this very big array we've got to go through, and that's taking lots of loads and stores. Are we doing that anywhere else? Are there ways we can cut that down? Are we sure we're doing this in the most optimized way? And then go through that as well. You also have things like array syntax in Fortran, which is very nice from a programming point of view, but makes it hard for the compiler to do some of this. So these array syntax here will actually by the compiler be turned into a big loop, but it won't fuse those things together. So there can be some optimizations if you're doing Fortran programming to have a look at getting better, redesigning how you implement this to get better performance as well. So here's some examples here. We've got two subroutines. We call subroutine 1 and subroutine 2. And inside subroutine 1, we go all the way through A and B. And we can imagine that subroutine 2 is doing the same thing we saw before, which is taking A and adding something onto it. And if we call this one after the other, we haven't merged those loops, because so they're going to go all the way through again. Whereas you could actually have that where you have those subroutines called for small chunks of the work, and you get back to that merging the thing. So the data that's being loaded up in subroutine 1 will be staying in cache while subroutine 2 is run. And so those are the kind of things you can do as well. And then finally, there is all this idea of prefetching. So some processors, like the ones we have on ARCHER2, these AMD ROMs, will do prefetching for you. So it will learn the pattern of data you're loading. If it's a simple pattern, like I'm loading the next dimension of my array, I keep loading the next dimension of my array, it will do that for you, and it will preload the data in advance of you actually asking for it. And that can be good because you hide some of the access costs there. That only usually works for quite simple applications, quite linear accesses, and so there are ways you can optimize that, either by putting prefetch instructions in to change, to manually configure that, or doing things like loading up these huge pages, which lets it do the prefetching on large data structures. So there's a module on ARCHER2 called Create Huge Pages, which will let you do, will try and optimize the memory allocation in such a way that that costs less and enables more preloading and prefetching of data as well. As we have looked on in the vectorization thing, for performance, this idea of pointer aliasing is bad, and we saw that yesterday. It's in C, we can use this restrict keyword to help it out. In Fortran, there isn't as many pointers, but you can have pointers in Fortran. So again, with Fortran, if you can try and avoid using pointers in performance critical parts of code, that can be helpful. In C, you can use this restrict keyword to tell the compiler, for this function, these pointers don't overlap, so you can optimize assuming that they don't overlap. And you can also use these compiler flags to say actually for the whole code there isn't any overlapping, so you can assume there isn't and do your optimizations based on that. Okay, so that's a pretty whistle-stop store through memory optimizations and memory challenges. In this case, the important thing to remember is that layout. If you've got multi-dimensional arrays, making sure you're accessing them in a contiguous order, if possible, for your algorithm, will give you the best performance. And that can be a very significant performance benefit or hindrance, depending on what you're doing there. And then there are some other things you can look at when you want to look at sort of more performance optimization at a low level, things like combining loops, combining subroutines, of these kind of approaches that we've discussed will also give you some benefits and can improve the performance of your program. And then alongside that, we've seen that a lot of the things we've talked about are quite common across compiler optimization, quite common across vectorization and memory optimization. So there's these common patterns of programming. The things that you've got simple loops, you've got loops without control structures in them, loops that are well defined and have good, iteration spaces, will all help your program get good performance on modern processors. Any questions? Okay, if there's no questions, what I will do is I will stop the presentation, and then there is a set of, let me share this other screen. There is also a practical around memory performance and cache blocking. So if you go into the exercises and have a look at the practical notes, we've got the memory bandwidth cache blocking exercises here, exercise 5 and 6 you can have a look at, to look at, what can you do to simple programs to check performance and improve their performance for memory cache blocking optimizations. So have a look at those, and I'll be around here. Just let me know if